of Downtown Lectures sponsored by the Peter Wall Institute for Advanced Studies at the University of British Columbia. And the Institute itself is dedicated to advancing innovative and fundamental research that can generate new ideas, new thinking, and ultimately important contributions to society. The Wall Exchange's objective is to help us collectively engage in conversations about important and timely issues with about our global society, and tonight's conversation promises exactly that. I'd like to thank the Georgia Straight Magazine for co-sponsoring this event, and to thank CBC Radio 1 Ideas Program, producer Yvonne Gall and her crew for taping the event for a future Ideas broadcast. The program this evening: Lord Rees will speak for 45 minutes. Bob MacDonald will then serve as moderator for a 45-minute question and answer. Bob MacDonald, who's probably known to everyone in this audience, is a Canadian author and the national science journalist and commentator for CBC Television and News Network. Since 1992, he's been the host of a very popular science radio show, Quirks and Quarks. Thank you, Bob, for your willingness to serve this evening. Behind me on your screen, you can find our Twitter handle. We're moving into the modern ages, and the hashtag WallX. So in addition to the microphones later this evening at the front, we'll be taking questions via the hashtag WallX, and you can send your questions in during the lecture or for the first 2 minutes afterwards, and Bob will post some of those in addition to the questions at the mic. Now to introduce Lord Martin Rees. Baron Rees of Ludlow is a cosmologist and astrophysicist. He received his doctorate at Cambridge and has taught at Sussex University and Cambridge University. In 2005, he was elevated to the House of Lords. He has been the UK Astronomer Royal since 1995 and has been Master of Trinity College for a number of years, having just recently stepped down from that post. He's been president of the Royal Society. He's a well-respected author of books on astronomy and science, and in 2010 he delivered the prestigious Rees Lectures for the BBC. Lord Rees was one of the first to propose that enormous black holes power quasars, and that superluminal astronomical observations can be explained as an optical illusion. In recent years, he has worked on gamma ray bursts and how the cosmic dark ages ended with the first stars were formed. In a more speculative vein, he has been interested in anthropic reasoning and the possibility that our visible universe is part of a vaster multiverse. Lord Rees believes in the search for extraterrestrial intelligence, that it's worthwhile, but even though its chance of success is small. Of tonight's lecture, A Cosmic Perspective for the 21st Century, Lord Rees has said, "The Earth has existed for 45 million centuries, but this is the first when one species, ours, can determine the long-range planetary future." Please join me in welcoming Lord Martin Rees.
Good evening, ladies and gentlemen. I always have to say that I'm not an astrologer. You'll get no horoscopes from me. But towards the end of this talk, I am going to look forward into my very cloudy crystal ball and share some hopes and fears on what our lives might be like 50 years hence. But I am an astronomer, and I'll set the scene by saying something about a cosmic perspective. Let me see it. Yeah. Right. Astronomy is the oldest science, except perhaps for medicine. And at the risk of offending any medics here, I claim it was the first science to do more good than harm. Ever since ancient times, it's been crucial for the calendar, for timekeeping and navigation. And it's the grandest of the environmental sciences. Indeed, the night sky is the only part of our environment that's been shared by all humans throughout history. They've all looked up and wondered at the stars and interpreted them in their own way. But as a science, astronomy is slightly more recent. And it took a big step forward here. This is my college in Cambridge, through the work of the best student we ever had, Isaac Newton. Trinity's been in decline ever since. There's been no one as good as him. But I have to say that though he was an unparalleled intellect, he was a most unpleasant man, solitary and reclusive when young, vain and vindictive in his later years. But he did design the first reflecting telescope, and he must have thought about reaching for the stars, because this is a picture from the English version of his great book, The Principia. And it's still the neatest way to explain the concept of orbital flight. He calculated that for a cannonball to achieve an orbital trajectory, for its trajectory to curve downwards no more steeply than the Earth curves away underneath it, its speed must be 18,000 miles an hour, far beyond what was then achievable, of course. And as everyone knows, the first object to achieve orbital speed was Sputnik 1, launched by the Soviets in 1957. 4 years later, Gagarin was the first man to go into space, and only 8 years after that, we had this familiar, iconic picture. And this was only 66 years after the Wright brothers' first flight. And I cherish this picture, signed for me a few years ago by 7 of the Apollo astronauts. It's not signed by Neil Armstrong, but I did meet him, actually. He, in fact, was sitting in the front row taking notes when I once gave a lecture in Philadelphia. At least I thought he was taking notes. He might have been doing the crossword or something. I don't know. But, of course, this was a heroic episode. And had the momentum been maintained over the next 40 years, after Apollo, there would be footprints on Mars by now. But after Apollo, as we know, the political impetus for manned spaceflight was lost. And it was a long time ago. Ancient history to today's young people. My students in England know that the Americans landed on the moon. They know the Egyptians built pyramids. But both enterprises seem driven by equally arcane goals. Because since 1972, people have done no more than circle the Earth in low orbit, more recently in the International Space Station. But space technology, without people, has of course burgeoned for communication, environmental monitoring, sat-nav and so forth. We depend on it every day. And for science, it's been crucial too. Telescopes in space and probes to the other planets, bringing back pictures of varied and distinctive worlds. So let me give you a quick tour of the solar system. This is a picture taken on the way to Mars, looking back from 5 million miles at the Earth and the Moon, where the sun's coming from the right. When you get to Mars, here are some pictures taken with the European Mars Express. This is a gorge several kilometers deep. This is evidence for some changes, sort of landslides on the surface. Things are changing from month to month. And, of course, in August, the Curiosity rover landed, and for the next 10 years, it'll be trundling around on the surface of Mars. It landed in the top left, and it's going to be going through this vast crater, ending up climbing the geological strata of the mountain in the middle. Going beyond to the outer solar system, here's Jupiter. The 4 moons discovered by Galileo all have been observed close up, and they're all very different. This is Io, sulfurous and volcanic. This is Europa, covered in ice with probably an ocean underneath, and there's a close-up of some of the ice. Going still further, the Cassini spacecraft went to Saturn. It sent back this wonderful picture from beyond Saturn. This shows an eclipse of the sun by Saturn. The Cassini is beyond Saturn lined up so that Saturn blocks out the sun and you can see the rings in sunlight. That's a beautiful picture. Here's another picture. Something else that Cassini did was it carried in its cargo bay a small probe called Huygens, a robotic probe that was supposed to land on Titan, the giant moon of Saturn. And indeed it did. Titan has an atmosphere, it lands with a parachute. On the way down, it took the two pictures, the left and the middle. The right is where it landed. Now, this might look a rather nice place, rivers and a little lake, but the temperature's minus 160 degrees centigrade, and those rivers are liquid methane, and those lumps on the right are lumps of methane ice. Well, I hope that during the coming decades, by 2050, the entire solar system will have been explored and mapped by flotillas of tiny robotic craft. But will people follow them? This is Harrison Schmitt, one of the last people on the moon, 40 years ago. And I think the practical case for sending people back into space gets ever weaker with each advance in robotics and miniaturization. Indeed, as a scientist or practical man, I see little purpose in sending people back into space at all. But as a human being, I'm an enthusiast for manned spaceflight, and I hope some people now living will walk on Mars. They may be Chinese. China has the resources, the dirigist government, and maybe the willingness to undertake an Apollo-style program that leapfrogs what the Americans did. But if others boldly go to the moon and beyond, I think it's more likely to be via cut-price ventures, spearheaded by individuals prepared to accept high risks, perhaps even one-way tickets. When I'm a bit older, I'd accept a one-way ticket. And they'd be driven by the same motives as early explorers, mountaineers, and the like. And that's why I'm hugely enthusiastic about Elon Musk's SpaceX company and other companies fronted by entrepreneurs with resources and high-tech expertise. By the way, I think the phrase space tourism should be avoided. It lulls people into thinking that such ventures are routine and low risk. And if that's the perception, the inevitable accidents will then be as traumatic as those of the space shuttle were. Instead, these cut-price ventures must be sold as dangerous sports or intrepid exploration. And they'll just be for the few. Don't ever expect mass emigration. Nowhere in our solar system offers an environment even as clement as the Antarctic or the top of Everest. Space doesn't offer an escape from Earth's problems. But having said that, a century or two from now, there may be small groups of pioneers living independently of the Earth, on Mars or on asteroids. And whatever ethical constraints we impose here on the ground, we should surely wish such pioneers good luck in genetically modifying their progeny to adapt to alien environments. And that'll be a step towards a divergence into a new species. The post-human era will then begin, perhaps only in a few hundred years. And this leads to one of the great unknowns. What creatures might be out in space already before we get there? No one expects much in the solar system. There are a few places here where there might be some life, but no one expects anything very advanced in these locations. But now, let's widen our gaze from our solar system to the world of the other stars, far beyond the reach of any probe we can now conceive. Prospects are here far brighter. We've now learnt something that makes the night sky far more interesting than it was to our forebears. We've learnt that the stars aren't just twinkling points of light. Many, perhaps most of them, are orbited by retinues of planets, just like the sun is. This is a really fast-moving field of science. And these planetary systems display a surprising variety. Sometimes you find planets as big as Jupiter orbiting very close to their parent star, so their year will be a few days. Some are on very eccentric orbits. one planet, several planets are orbiting binary stars. So they'd have two stars in their sky, and just in a newspaper today, I read about a discovery of a planet that would have 4 suns in its sky. So a remarkable variety already being found, a very exciting subject. But essentially all this evidence about planets around other stars comes indirectly, not by seeing the planet, but by seeing the effect of the planet on the motion or the brightness of the star it's orbiting. And I just want to talk about one technique, the technique where you look for changes in the brightness of the star. And this theory here is very simple. If a planet moves across in front of a star, it blocks out a bit of the light. So if you measure the brightness of the star, it'll drop a little bit when the planet's transiting. If, for instance, you looked at a transit of the Earth across the Sun from a great distance, the dip would be 1 part in 10,000. And the Kepler spacecraft, launched 3.5 years ago, has been pointing at the same part of the sky and measuring the brightness of about 150,000 stars in that part of the sky to a precision of 1 part in 100,000, and doing that several times an hour for each of them, looking for cases when you see these periodic dips, indicating a planet whose orbit's in the plane of the sky going across. And this is the way in which we have found huge numbers of planets, or at least found their shadows. Again, we haven't seen them directly. But we would, of course, really like to see these planets. This is just a movie of what we'd like to see. And that's very hard. To realize how hard, let's suppose there were some aliens out there, say 30 light years away, and suppose they were looking at our solar system with a very big telescope. To them, the sun would look an ordinary star, and the Earth would look, in Carl Sagan's nice phrase, as a pale blue dot, very close in the sky to its star, our sun, and billions of times fainter. But if the aliens could look carefully at the pale blue dot, they could learn quite a bit about it. The shade of blue would be slightly different, depending on whether the Pacific Ocean or the landmass of Asia was facing them. So they could infer that there were continents and oceans, they could infer the length of the day, and something of the climate and seasons, and maybe by looking at the light very carefully, something about the atmosphere and that there was oxygen and ozone. Well, we can't do this yet, but within 20 years, telescopes like this will be able to do just that sort of thing for Earth-like planets around other stars. This is a telescope which the Europeans hope to build, where the mirror will be a mosaic 39 meters across. That's about twice the width of this room, really huge. And that will be able to do this sort of thing within 1 or 2 decades. Well, will there be life on any of these extrasolar planets? We can't assess the odds. Indeed, how life began on Earth is still unfinished business for scientists. We don't know. It could have been inevitable, or it could have been a rare fluke, like shuffling a deck of cards and ending up with them in perfect order. I hope we'll understand by 2050 how life began on Earth. And that, of course, will give us some handle on how likely it is to have arisen elsewhere, and also clues as to where to look. Even if simple life were common, and it may be, it's of course a separate question whether on these other worlds it's likely to have evolved into anything we might recognize as intelligent or complex. And it might be too parochial to focus on Earth-like planets and creatures like us. Science fiction writers, of course, have many other ideas. Balloon-like creatures floating in the atmosphere of Jupiter-like planets, swarms of intelligent insects, nanoscale robots, and all kinds of things. And incidentally, I would advise students it's better to read first-rate science fiction than second-rate science. It's much more fun and no more likely to be wrong, and it stimulates your imagination. Well, I'm not holding my breath for the detection of extraterrestrial intelligence, but I'm glad some people are looking. If we detect a signal that's plainly artificial, then, even if it's very boring, a list of prime numbers or the digits of pi, then it will carry the momentous message that concepts of logic and physics, if not consciousness, aren't limited to the hardware in human skulls, as it were. I don't think we know yet. But I wanted to mention that, of course, there are some people who think they do know the answer. They're the people who think they've been visited by the aliens and they've seen UFOs. And I get letters from such people. It's one of the results of being Astronomer Royal. And I tell these people two things. First, I ask them, is it really likely that if these aliens had made the huge technological effort to cross interstellar space, that they would just meet a few well-known cranks, despoil a few cornfields with corn circles, and go away again? I think it's unlikely. And the second thing I tell them is to write to each other and not to me. Well, we might find ET, but perhaps ET doesn't exist. Earth's intricate biosphere may be unique, and that may disappoint the searchers, but it would have its upside, because it would entitle us to be less cosmically modest, because our tiny planet could then be the most important place in the galaxy. Perhaps even a seed from which life in the far future could spread through the galaxy. The philosopher Wittgenstein famously said, if a lion could speak, we couldn't understand him. So even if we found aliens, would the culture gap with them be unbridgeable? I don't think it would necessarily. They may come from planet Zog and have 7 tentacles, but science would be a common cosmic culture. They'd be made of atoms just like us. They'd gaze out, if they had eyes, at the same cosmos. They'd trace their origins back to the same Big Bang. But of course, if we get a signal, we've got plenty of time to think of a good response, because signals take many decades to get there and back, so there's no scope for snappy repartee, as it were. But we could talk about the cosmos, so let me now offer a few comments on how we are probing the cosmos on the wider scale. First, a few words on stars. We understand a lot about stars, how they form in places like this, the Eagle Nebula, where new stars are condensing from dusty gas. We also see stars dying. This is what the sun will look like in about 6 billion years. And bigger stars die explosively. This is a famous object. Many people will recognize it. It's called the Crab Nebula. It's the expanding debris from an explosion of a star, supernova, witnessed by Chinese astronomers in the year 1054 AD. Some people here can perhaps read this, but I've been told this is the record of the Emperor's court astronomer saying that the guest star had appeared in the heavens, brighter than the moon, and disappeared after a few weeks. And when we look to that place in the sky, we see 1,000 years later this. Now, you might think these supernovae are far away and long ago and irrelevant, but were it not for these, we wouldn't be here. That's because stars, during their lifetime, derive their energy via nuclear fusion. They turn hydrogen into helium, into carbon, into oxygen, etc. And then they fling it back into space. And then from that debris, new stars form. So all the atoms in our body were forged in ancient stars that lived and died before our solar system formed. Indeed, almost certainly each of us has atoms in us from hundreds of different stars from all over the galaxy. So we are literally the ashes of long-dead stars, or if you're less romantic, we are the nuclear waste from the fuel that made stars shine. And our galaxy is like a sort of ecological system where gas is being churned from one generation of stars to another. If you could get 2 million light years away from the Earth and look back, we'd see our galaxy looking like this. This, of course, is Andromeda, the nearest big galaxy to us. It's a disk viewed obliquely, where 100 billion stars are orbiting around a central hub, in the middle of which lurks a black hole weighing 30 million suns. And these galaxies are the main ingredients of the large-scale cosmic scene. Here's another one. This is the Whirlpool galaxy. Now, we can see lots of galaxies like this, and you might ask, how can we learn anything about them? Because they take about 100 million years to turn around. We can't experiment on them. If we are studying particles, we can crash them together in an accelerator and see what happens. We can't do that with galaxies, except that we can in the virtual world of our computer. We can model two galaxies, the gravitational pull of every star and every other star, and see what happens. And this is a movie showing that. Two galaxies are falling together, and you get a sort of train wreck. And it comes a mess like that, and this will settle down into one big amorphous galaxy. I should warn you that the Andromeda galaxy that I showed is going to crash into our galaxy in about 5 billion years. And our galaxy will end up looking like this. Now, we can look up into the sky and look at lots of galaxies, and we see some like this. This is a real picture of two galaxies. And having done those sorts of calculations, which are speeded up by 10 to the 15 from real time, we can infer that what's happened here is two galaxies have got dangerously close, and each has raised tidal plumes on the other. And if we came back in 100 million years, we see these two having merged. So we can understand galaxies by modeling them and then looking at examples. There are huge numbers available for study. And we can also see what they were like in the past by looking far away and therefore far back. This picture shows a little patch of sky, a patch so small it would take 100 patches like it to cover the area of the full moon. If you had a small telescope, you'd see just a bit of blank sky. But with a big telescope, you see hundreds of smudges here, each one a galaxy, many fully the equal of our own or Andromeda, looking so small and faint because they're so far away. They're being seen at a distance of 10 billion light years when they've only recently formed. And this is observations out towards the limits of our observable universe. Now, one thing we've realized, and this was alluded to in the introduction, is that our universe, the physical reality, may be even bigger than we thought. We can look out to these galaxies 10 billion light years away, but we get to a horizon. The horizon is set by how far light's been able to travel since the Big Bang. But that horizon isn't anything real, any more than if you're in the middle of the ocean, the horizon around you is real. If you're in the ocean, you think the ocean goes on a lot further. And likewise, we suspect that the universe goes on a lot further than we can see. As in the bottom right here, we look out 10 or 50 billion years, but there are lots and lots of galaxies before. We have good reason for thinking that they go 1,000 times further, and they may go far, far further still. Indeed, if space stretches far enough, all conceivable chains of events could be played out somewhere, all combinatorial options. There'll be replicas of ourselves, monkeys will type the works of Shakespeare, and whenever a choice has to be made, one of the replicas of ourselves will take each option. So if you make a bad decision, maybe it's a consolation that somewhere out, far beyond the horizon, you've got an avatar that's made the right decision. But that's not all. I've talked about that volume, which is the aftermath of our Big Bang. It may be that our Big Bang is not the only one. There's the idea of the multiverse, and that's depicted as a cartoon here, where this is our Big Bang, and there are other domains of space and time quite separate from ours. And the best studied of this is called eternal inflation, where Big Bangs are continually popping off in an expanding substratum. Well, this is all very speculative. Firming it up requires understanding the physics of the early hyperdense stage of the universe. So I put a hazard sign here because this is not well established. We can actually confidently extrapolate the universe back to when everything we can now see with our telescopes was squeezed down to the size of a solar system. At that time, each particle would have the same energy as we could produce in the LHC at Geneva. But all the key properties of the universe were laid down much earlier still, when the universe was that big. And I like this cover of this journal, which says that the universe was once that big. And that's when many key features of the universe were, we suspect, imprinted. So, we've learnt that we live in a solar system that's just one planetary system among billions, in one galaxy among billions. But perhaps further Copernican demotion confronts us. The entire panorama that astronomers observe could be just a tiny segment in the aftermath of our Big Bang, which is in itself just one Big Bang among a perhaps infinite archipelago. And incidentally, what we think of as universal laws may, in this even grander perspective, be just parochial bylaws in our cosmic patch, a patch that happens to extend more than 10 billion light years around us. Well, it's exhilarating that these concepts are not just metaphysics, they're speculative science, but they're within the scope of scientific inquiry. And I think within 50 years, we will perhaps be able to say firmly whether we are part of a multiverse. But we're still groping for the truth, where in the fashion of ancient cartographers, we must still say, "Here be dragons." We confront Donald Rumsfeld's famous unknown unknowns. And what a pity, incidentally, that he didn't stick with philosophy. If I needed a logo for my area of research, I'd choose this. It's called an Ouroboros. It depicts the interconnectedness of the microworld on the left, of neutrons, atoms, and cells, and the cosmic world of stars and galaxies on the right. And we learn a great deal about the unity of things because of the links between left and right. The everyday world is determined by atoms, how they stick together to form molecules. Stars are powered by the nuclei within those atoms. There's a link there. And though I haven't had time to discuss it, we believe that atoms, the galaxies are held together by dark matter, which is made up of some subnuclear particles left over from the Big Bang. So there's a link there. The left-hand side here is the domain of the quantum. The right-hand side is where gravity and Einstein's theory holds sway. And those two theories, gravity and quantum theory, are the two great pillars of 20th century science. But they haven't yet been meshed together into a single theory. And in most contexts, this doesn't matter, because the domains of relevance don't overlap. Astronomers can ignore the quantum fuzziness in the orbits of planets because they're so big. Conversely, chemists can ignore the gravity between the atoms in a molecule because they're 40 powers of 10 weaker than the electric forces. But if we want to understand the very beginning of the universe, when the universe was itself very small, then we do have to have this unified theory. We need to have the unification symbolized, as it were, gastronomically here, because when the universe is very small, quantum fluctuations could, as it were, shake the entire universe. So to confront the overwhelming mystery of what banged and why it bangs, we need this theory, sometimes called the theory of everything. We ourselves, here, are midway on a log scale between atoms and stars. We're large enough compared to atoms to have lots of complexity, but not so large that we're crossed by gravity. And we are actually midway. It would take as many human bodies to make up the sun as there are atoms in each of us. The geometric mean of the mass of a proton and the mass of the sun is 50 kilograms, within a factor of 2 of the mass of each person here. And so to understand ourselves, we need to understand the atoms we're made of. We also need to understand the stars that made those atoms. And I mentioned the frontier of the very small and the very large. unified up here. But there's a third scientific frontier, the very complex. And this is, in a way, the most challenging one. Even an insect, with its layer upon layer of complexity, is harder to understand than a star or an atom, where intense heat and compression in a star precludes complex chemistry. This, incidentally, is the famous flea drawn by Newton's least favourite colleague, Robert Hooke, who was the pioneer inventor of the microscope and a wonderful draftsman, and he produced this book in the 1660s drawing the flea and other insects through his microscope. So unified theories of the very large and the very small, though of course a huge challenge to science, shouldn't really be called theory of everything. That's a hubristic and misleading term because they're irrelevant to 99% of scientists who work on things that are very complicated. Most scientists working on things down here are not held up at all by not having a unified theory. They're held up because they're studying things that are just very complicated. And that, I think, is important. A certain modesty is needed on the part of theoretical physicists. The analogy is often given of a game of chess. Suppose you'd never seen chess being played before. Then by watching play a game, you could infer what the moves were, how the knight moved, how the bishop moved, etc. But in chess, learning how the pieces move is just a trivial preliminary to the progression from novice to grandmaster. Likewise, learning the basic laws that govern the elementary particles is just a preliminary to understanding how these manifest themselves in complicated structures, including the most complicated we know about, which are these things here. Nearly all scientists are reductionists insofar as they think that everything, however complicated, obeys the basic equations of physics. But even if we had a hypercomputer that could solve those equations for, say, breaking waves, migrating birds, or human brains, it wouldn't yield the kind of explanation we really seek. Phenomena with different levels of complexity are understood in terms of different irreducible concepts: turbulence, survival, alertness, and so forth. The brain is an assemblage of cells. A painting is an assemblage of chemical pigment. But in both cases, what's important and interesting is the pattern and the structure, the emergent complexity. Well, how far will we have got by 2050? 50 years ago, we didn't know if there was a Big Bang. Now, as I said, we can draw quite precise inferences back to a nanosecond. So in 50 years, debates that now seem flaky speculation may have been firmed up. But, and here I'm perhaps sticking my neck out a bit, I think we should recognize that at some stage we might, as it were, hit the buffers because our brains just don't have enough conceptual grasp. After all, our brains evolved to cope with life on the African savanna where our remote ancestors lived, and they haven't changed much since then. And it's surprising, therefore, that we've got so far in understanding the counterintuitive microworld of atoms and the vastness of the cosmos. But just as a monkey can't grasp quantum mechanics, there could be aspects of reality, unified theory or consciousness or something, whose elucidation must await some post-human intellect. Maybe these intellects are out there already. If not, they might emerge in the far future. Now, let me focus back on the Earth, as I will for the rest of my talk. I've lived my life among astronomers, and I can assure you that their awareness of vast expanses of space and time doesn't make them any more serene in their everyday life. They fret as much as anyone else about tomorrow and next week. But there is one special perspective that astronomers can offer, and that's an awareness of a vast future. The stupendous timelines of the evolutionary past, as in this time chart, are now part of common culture, except maybe in Kansas or parts of the Muslim world. But most people still somehow think that humans are the culmination of the evolutionary tree. We are the end of it all. And that hardly seems credible to an astronomer. I'll tell you why. As this time lapse illustrates, our sun formed 4.5 billion years ago. It's a bit less than halfway through its life. It'll be 6 billion years before it flares up, engulfing the inner planets. And the expanding universe will continue, perhaps forever, destined to become ever colder, ever emptier. To quote Woody Allen, eternity is very long, especially towards the end. So any creature witnessing the Earth's demise 6 billion years hence and sending this postcard, they won't be human. They'll be as different from us as we are from a bug. Post-human evolution, here on Earth and far beyond, could be as prolonged as the Darwinian evolution that's led to us, and even more wonderful. Darwin himself was aware of this. But we can strengthen the conclusion because evolution in the future is going to be even faster than in the past. It won't be natural selection, it'll be on the technological timescale of genetic modification or machines taking over. But even in this concertina time span, stretching billions of years into the past and billions into the future, this century is a defining moment. We've had these images for 40 years. They're iconic for environmentalists. But suppose that the hypothetical aliens I mentioned earlier, who are watching our planet, had been doing so for its entire history. What would they have seen? Over nearly all that immense time, 4.5 billion years, Earth's appearance would have altered very slowly. Continents drifted, the ice cover waxed and waned, successive species emerged, evolved, and became extinct. But in just a tiny sliver of the Earth's history, the last 1/1,000,000th part, a few thousand years, the patterns of vegetation started to alter faster. This signaled agriculture, the presence of humans on the scene. And then there were even more abrupt changes. The carbon dioxide in the atmosphere began to rise enormously fast, and something else completely unprecedented happened. Rockets launched from the planet's surface escaped the biosphere completely. Some went into orbit around the Earth, some journeyed to the moon and planets. Well, if they understood astrophysics, these aliens could have predicted that the biosphere would face doom in a few billion years, when the sun heated up and then flared up and died. But could they have predicted this sudden fever halfway through the Earth's life? These human-induced alterations occupying overall less than 1/1,000,000th of the Earth's elapsed lifetime and seemingly occurring with runaway speed. If they continue to keep watch, what might these aliens witness in the next 100 years? And the answer, of course, depends on us. The stakes are high between progress and catastrophe. Some years ago, I wrote a short book on this theme, which I entitled Our Final Century, with a question mark, and the publisher took away the question mark, as you can see. And then the American publishers changed the title to this. Americans like instant gratification, and perhaps the reverse. And my theme was that taking all risks into account, we wouldn't wipe ourselves out, but there was a 50% chance that we wouldn't get through to the end of a century without some disastrous setback. And just as a plug, I should mention my new book, which develops this in more detail. Over most of history, the threats to humanity have come mainly from nature. Disease, earthquakes, floods, and so forth. But this century is special. It's the first when one species, ours, has Earth's future in its hands and could jeopardize life's immense potential. We've entered a geological era called the Anthropocene. And the Anthropocene began, I suppose, with the advent of thermonuclear weapons. But devastation could arise insidiously rather than suddenly, through unsustainable pressure on energy supplies, food, water, and natural resources. Indeed, these pressures are the prime threats without enemies that confront us. Humanity's footprint is getting larger because we're becoming more demanding of resources. but also because there are more of us. This is how populations have grown over the centuries, very fast indeed, rising from 3 billion in 1960s to 7 billion today, and probably going up to between 8.5 and 10 billion by 2050. And most of the growth is going to be in the developing world, and the world's intellectual and physical capital is going to shift to Asia. It'll be the end of 400 years of European and North American hegemony. But the projected growth is slowing off a bit, because in many countries fertility has fallen to the replacement level of just over 2 births per woman. Indeed, in Europe it's only 1.4. And the falls have been dramatic in some places. In Iran, in 30 years, it's fallen from 7 down to 2. And this so-called demographic transition is a consequence of declining infant mortality, availability of contraceptive advice, women's education, and so forth. But numbers are still rising fast in some parts of the world. India's population is projected to overtake China's in 2030 and could exceed 1.6 billion by 2050. And there could then be 1 billion more people in Africa than today, where the fertility rate is still more than 7 in some countries. Global population seems a currently under-discussed topic. That's partly because doom-laden forecasts made in the past proved off the mark, and because it's deemed by some a kind of taboo subject, tainted by association with eugenics in the 20s and 30s, Indian policies under Indira Gandhi, and more recently with China's effective but hard-line one-child policy. There's a campaigning group in England called the Optimum Population Trust, which tries to promote interest in these issues, and I belong to it. But I'm not sure that we can actually specify an optimum population for the world. That's because we can't confidently conceive what people's lifestyles, diet, travel patterns, and energy needs will be in 2050 and beyond. To take 2 extremes, the world couldn't sustain anywhere near its present population if everyone lived like present-day Americans. On the other hand, 20 billion people could live sustainably with a high quality of life if they all had a vegetarian diet, didn't travel, and interacted just by super internet and virtual reality. Though that particular scenario is neither very likely nor very attractive. But it is therefore naive to quote a single unqualified headline figure for the world's carrying capacity. But nothing barring catastrophe can stop a rise to around 9 billion by mid-centuries, and that's because most people now alive are still young. But we can influence the trends beyond that time, and enhanced education and empowerment of women within this decade is surely a benign priority in itself, but it would reduce fertility rates in Africa and India. And that is surely a good thing, because the higher the post-2050 population becomes, the greater will be all pressure on resources, especially if the developing world, where most of the growth will be, narrows its gap with the developed world in per capita consumption of energy and other resources, as we surely hope it will. Humans appropriate about 40% of the world's biomass already, and that fraction is rising. And the resulting ecological shock and extinctions could irreversibly impoverish our biosphere, and these risks are aggravated by climate change. We are destroying the book of life before we've read it. Biodiversity is a crucial component of our well-being. We're clearly harmed if fish stocks dwindle to extinction. There are plants in the rainforest whose gene pool might be useful to us. But for many environmentalists, these instrumental and anthropocentric arguments aren't the only compelling ones. For them, preserving the richness of our biosphere has value in its own right, over and above what it means to us humans. But despite these concerns, most experts claim that modern engineering and agriculture can provide food and energy for 9 billion. And other advances, especially in healthcare and information technology, offer bright prospects. But there's a downside, which I also discuss in my book. The same technologies that promise so much also open new vulnerabilities. For instance, global society depends on elaborate networks, electricity grids, air traffic control, international finance, just-in-time delivery, and so forth. And unless these are highly resilient, their manifest benefits could be outweighed by catastrophic occasional breakdowns cascading through the system. And the threat is terror as well as error. Concern about cyber attack by criminals or hostile nations is rising. And there are such concerns too in the bio area. Advances in genetics offer huge potential for medicine and agriculture, but already the genomes for some viruses, polio, Spanish flu, and SARS, have been synthesized. And expertise in such techniques will become widespread, posing a manifest risk of bioerror or bioterror. And we're kidding ourselves, incidentally, if we think that all those with technical expertise will be balanced and cautious. Expertise can be allied with fanaticism, and will be individuals with the mindset of those who now design computer viruses. The global village will have its village idiots, and their idiocies can have global range. So, the huge empowerment of individuals or small groups by fast-developing technologies presents, I think, novel hazards, and will highlight the tension between security, privacy, and freedom. The technologies I mentioned up to now are those that already exist. But what about new ones that could be equally disruptive and transformative? Scientific forecasters have a rather dismal record. One of my predecessors as Astronomer Royal said space travel was utter bilge. And few in the 20th century envisaged the transformative impacts of the silicon chip or the double helix. The iPhone would have seemed magic even 20 years ago. So looking 50 years ahead, we must keep our minds open, or at least ajar, to what may now seem science fiction. For example, human nature and human character have changed little for millennia. Before long, however, new cognition-enhancing drugs, genetics, and cyborg techniques may alter human beings themselves. That's something quite new and disquieting because it could portend more fundamental forms of inequality if these options were open only to a privileged few. And we're living longer. Indeed, a real wild card in population projections is that future generations could achieve a really substantial enhancement in lifespan. This is still speculation. Mainstream researchers are cautious about the prospects of more than incremental increases. But such caution hasn't stopped some people, worried that they'll die before this nirvana is reached, from bequeathing their bodies to be frozen, hoping that some future generations will unfreeze them, resurrect them, or download their brains into a computer. You can have this done in California, and as cut price, you can have just your head frozen and not the rest of you. Well, I was once interviewed by a Californian group of these cryonic enthusiasts, cryonics they're called. And their society was called the Society for the Abolition of Involuntary Death. And I rather upset them by saying I'd rather end my days in an English churchyard than a Californian refrigerator. And they derided me as an old-fashioned deathist for saying this. What about robotics? Even back in the 1990s, IBM's Deep Blue computer beat Kasparov, the world chess champion. But robots can't yet recognize and move the pieces on a real chessboard as adeptly as a child can. So advances are patchy. But later this century, their more advanced successors may relate to their surroundings and to people as adeptly as we do. And then a new set of moral questions will arise. We accept an obligation to ensure that other human beings, and even some animal species, can fulfill their natural potential. So what's our obligation towards sophisticated robots? Should we feel guilty about exploiting them? Should we fret if they are underemployed, frustrated, or bored? Well, these are problems for the conjectural future, but as science empowers us more, there'll be a widening gulf between what it enables us to do and what it's prudent or ethical actually to do. That is my concern. But the biggest gap today is between what science allows us to do and what really happens in the political and economic world we inhabit. We don't need new inventions to improve the world, we just need proper applications of those we already have. And scientists shouldn't be bashful in proclaiming a hopeful message. We can truly be techno-optimists. The innovations that will drive economic growth, information technology, biotech, and nanotech, can boost the developing as well as the developed world. And modern engineering and agriculture can feed us all. That's all good news. But of course, the intractable politics and sociology engenders pessimism. All too often, the parochial and the immediate trump the global in the long term. Politicians look to their own voters and the next election. Stockholders expect a payoff in the short run. Medical research focuses on diseases of the rich, not enough on tropical diseases. There's a current slogan in England called, "We are all in this together." It's received with a certain cynicism by many of us. It comes from David Cameron. But we need to realize that we are all on this crowded world together. Problems caused by shortage of food, water, resources, and the transition to a low-carbon economy can't be solved by each nation separately. So the question is, can our sympathies become more broadly international? Can our institutions prioritize projects which are long-term by political standards, even though a mere instant in the history of our planet? Well, I want to close with a bit of preaching, a personal perspective which strikes me whenever I visit the vast and ancient cathedral of Ely, which is just about 10 miles from where I live in Cambridge. This is 900 years old. Most of its builders had never travelled more than 50 miles. The fens were their world. Even the most educated knew of essentially nothing beyond Europe. They thought the world was a few thousand years old and that it might not last another 1,000. But despite these constricted horizons in both time and space, despite the deprivation and harshness of their lives, despite their primitive technology and meager resources, they built cathedrals, though they knew they might not live to see them finished. And their legacy still elevates our spirits nearly a millennium later. What a contrast this is to so much of our discourse today. Unlike our forebears, we know a great deal about our world, and indeed about what lies beyond. Many phenomena still make us fearful, but the advance of science spares us from irrational dread. We know that we are stewards of a pale blue dot in the vast cosmos, a planet with a future measured in billions of years, whose fate depends on humanity's collective actions. But all too often, our focus is short-term and parochial. We downplay what's happening even now in impoverished, far-off countries, and we give too little thought to leaving a fair inheritance for our grandchildren. So we do need to broaden our sympathies in both space and time, to perceive ourselves as part of a long heritage and stewards for an immense future, and to be guided by the best science, but also by values that science itself can't provide. The future is up to us. And just to finish with, I want to quote from the great biologist Peter Medawar. He said this, I quote, "The bells that toll for mankind are like the bells of alpine cattle. They are attached to our own necks, and it must be our fault if they do not make a tuneful and harmonious sound." Thank you.
Good evening, everyone. And thank you very much for coming and joining us tonight. Thank you, Sir Martin, for that wonderful, inspirational talk. Sir Martin Rees. I cannot tell you what a pleasure it is for me to be sitting here. I never thought I would find myself sitting in such presence. And the way this is going to work is we are opening this up to you. We have 2 microphones on either side of the stage at the bottom of the aisles. And if you have questions, please identify yourself as you come up to the mic, and please ask a question. Please ask a question. And I'm going to be really hard on that. But before we do that, I have a couple of questions myself. So Martin, as someone who studies cosmology, the grand scale of the universe, black holes in the centers of galaxies, you get to play with our most impressive technology to look at the universe. Does it ever bother you that 95% of it is still missing?
It doesn't really, no. I think, well, let me say 2 things. First, the advances we've made in the last 50 years are due to advance in technology. Better computers, better instruments for detecting faint light. Armchair theory doesn't deserve much of the credit, and that's all I do. But what we've learnt is that there's a lot of stuff out there that doesn't shine. There's so-called dark matter, about which we know quite a lot. We know how it behaves, we know how it clusters, and we know it's some sort of particles made in a Big Bang, which have no electric charge and don't interact with each other. So dark matter, I think, has to be there, and it's not a big problem. There is something which is sometimes called dark energy, and this is something which is a mysterious property of space itself. It seems that in space itself, even when you take everything away and it's completely a vacuum, there's still a sort of repulsive force which is too weak to have any effect on Earth or even in the galaxy, but on the scale of the cosmos, it pushes things apart at an accelerating rate and overwhelms gravity. And this, I think, is something we won't understand until we have the kind of unified theory symbolized by the snake eating its tail, because I think we have to understand the nature of space itself. And most people think that just as you can't chop up this table indefinitely, you get down to individual atoms. They think you can't chop up space or time indefinitely. You get down to a scale where there's a certain graininess. But the problem is that the scale on which space and time are grainy is very, very small, a billion times smaller than an atomic nucleus. We're very far from understanding that. But many people suspect that if you could magnify a bit of space, so if you look at what you think is a point, then on that tiny scale, what we think of as a point is actually a tightly wrapped origami in 5 or 6 extra dimensions, which we don't see because they're rolled up. And this is what's called string theory, which is a very difficult theory which is still speculative. But I think we won't understand this force accelerating the expanse of the universe till we've got that theory. So that's a big challenge, which is, I think, further in the future.
Then what? What if we do the grand unification theory? What if we get the theory of everything and it all comes together, the very large, the very small? Where do you go from there?
Well, then, as I said, it's like if you're watching chess being played, you've learned the rules of the game. And then you've got to explore the consequences of those rules in complicated games. We've got to explore how the laws manifest themselves in the amazing variety of things, stars, planets, and the biospheres. And also, we want to explore how much there is beyond what we can see. Is there really a multiverse or not? But I think it's important that physics is just the rules of the game, and the way those rules are manifested is what's really complicated, and that's complicated structures like us and any aliens that may be out there.
I'd like to bring it back down to earth, and I just came from a wonderful event. Sharon and I just came from Jasper Park, and it was the 2nd annual Jasper Dark Sky Festival. We have in Alberta, in Canada, the largest dark sky preserve in the world. And that's also why I'm wearing these funny shoes. We just came from there this morning. But about 500 people showed up for this event. People came out to look at the dark sky, and it was a wonderful thing. The storytellers were telling us about the constellations. We had telescopes. People were lining up for the telescopes. So there's obviously a public interest in science. But I also had somebody come up to me and say, well, I'm not into astrology, but I like what you do. And I had someone else, ask the difference between a planet and a galaxy. And there's a fundamental problem that I'm seeing, and I'm wondering about your interpretation on this, where people aren't getting the basics. Yeah. Information rich knowledge poor. We're awash in information, it's in your hand, but I'm finding people don't understand the basics. What's your take on that?
Well, first, can I say that it is indeed the case that astronomy has a very wide following. Everyone can enjoy the night sky. Lots of people with small telescopes can do a lot. And incidentally, they can now, as citizen scientists, make discoveries. For instance, the discovery of a planet with 4 suns in its sky, reported today. This was done by 2 amateurs in the United States who they were given a stretch of data taken by the Kepler spacecraft, the brightness time series for one of the stars, and they just found this complicated pattern there. So that's an example of how there's more opportunity for individuals to participate in science. So that's a great educational thing and wonderful for people to make discoveries. But going back to what you said, it is indeed remarkable, really, and I think when I go to the United States, it's got so many good scientists, but so much sort of anti-science, etc. at the same time. But I think we scientists shouldn't always be in grumbling mode, because the ignorance is all pervasive. I mean, it's true, it's sad if as you say, people don't know the difference between astronomy and astrology, if they don't know the difference between a proton and a protein, and many don't. But it's equally sad if they can't speak their language properly, if they can't find Syria or Afghanistan on the map, or don't know anything about the history of their country. And that's equally true of many people. So I think what you're highlighting is that there's a huge gap between the amount of information that's available and accessible to everyone and the amount that actually sinks into their heads.
But there's another problem beyond that, and that is determining the difference between the real science and the pseudoscience.
Absolutely, yes. And I think this is a problem, especially with the internet, because there's a huge amount of undigested stuff which is very confusing on the internet, and this comes up in climate science especially. But I think what we have to remind people is that if you have some disease and you look on the internet for the appropriate cures, you don't attach equal weight to everything you find on the internet. If you've got any sense, you entrust yourself to someone with some credentials in the subject. And likewise, one should react to the information and debate on any subject in the same way. You should attach more weight to people who have some sort of credentials and success rate in the subject, and not equal weight to all. And it's hard, of course, for people coming to the internet and being swamped by all this information to know how to do that, but that's what we should try to do.
The difference between scientific information and someone's opinion.
Yep, absolutely. Right. Yeah.
Let's go to the microphones. Gentleman over here on the far side.
My name's James Raymond. I'm actually a research analyst with the Vancouver Economic Commission. I'm incredibly concerned about geoengineering, as it seems likely that we might be the only intelligent life in the universe. I think we have a special duty to preserve what life we have here. I wonder if Sir Martin believes that we're in danger of potentially extinguishing the life that we have on this planet in future.
Right. Well, of course, I didn't say much about climate change, but again, as I'm sure everyone here knows, the one uncontroversial statement is that the carbon dioxide concentration is rising, and that is due to anthropogenic effects, and that in itself is warming up the atmosphere. The big uncertainty is what the so-called feedback effects are. Does the water vapor amplify that by a big factor or not? So we know that the climate is warming, we don't know how much. And if we don't cut down our CO2 emissions, then the projections are for this continued warming. And geoengineering is the idea that we can compensate for it by, for instance, putting lots of dust or something into the upper atmosphere, like an artificial volcano, and that'll stop some sunlight going down. And so that would cool down the Earth despite the rise in CO2. But it would store up problems for the future, because if we ever stopped putting the stuff up in the atmosphere, then we get a very sudden warming. And also things like ocean acidification would still go on. So I think we do need to make people care about what happens 100 years from now if we don't cut our CO2 emissions. It is true that we can't be absolutely confident that the temperature will rise at a disastrous rate, but as an insurance policy, we should take precautions against it. If you ask what I think will actually happen, my suspicion is that there'll be very little effective action in the next 20 years. Annual CO2 emissions will probably go on rising. But 20 years from now, we'll know for sure how fast the temperature is rising because of CO2. If we are on the lower trajectory, where the rise is gradual, people will relax. If we are then on the higher trajectory, then there'll be a panic and there'll be strong pressure for geoengineering. But of course, as you imply, it's going to be something which is going to store up problems for the more distant future.
Thank you very much. Here's a question from Twitter. Dr. Rees, how do you feel about the ingenuity of humans versus pre-designed robots to perform tasks in space?
Yes. Well, of course, humans are, in general, way ahead of any pre-designed robot. But on the other hand, if you think of the value for money, then to send a robot, which you don't have to bring back, is a good deal cheaper. So it is true, and someone has said that a trained geologist could do as much in a few weeks as Curiosity will do trundling around for 10 years. That's certainly true. But to send one geologist would be more expensive. But the other point I would make is that if we project 20 years from now, then robots will be far more sophisticated. So I still don't think there'll ever be a scientific case for sending people into space, because the robots are catching up and will be more cost-effective compared to humans. So, as I say, I think the only case for humans going is just as a sport or as an adventure.
Why not have fun? I'm
Yeah.
all for that. Person here, yes, sir.
Duncan Graham. Just a big question on the universe. I read in the book The Echo of the Big Bang that knowing that the universe is flat. Could you tell me the shape of the universe?
Shape of the universe.
Well, okay. Well, it's true that that term is used. It's used in a slightly technical sense. What that means is that just as the difference between a flat table and a sphere is that if you draw a triangle, the angles add up to 180 degrees on a flat surface, but more on a sphere. Then we can do the same for a big circle a big triangle in the universe. And it turns out that the angles of any triangle in the universe add up to 180 degrees. So in that sense, it is flat. And so that's a simple kind of cosmological theory which is fulfilled, because we can now look at very distant objects and measure the angle between them, etc. And we do know with high precision that it does have this property.
But then, as you said before, since we have a horizon we can't see over, we don't really know what shape the universe is.
Well, no. We only know the shape of the part out to our horizon,
well, we can see.
And we don't know what lies beyond. But just to expand slightly what I said I thought we could confidently say that the galaxies go on thousands of times further than we can see. And the reason I said that is that if you look as far as you can in one direction and the opposite direction, then the conditions in those two directions don't differ by more than 1 part in 100,000. So that means that if we're in some huge finite entity, then the gradient across it is very gentle. And it probably goes on a lot further. But it could go on much more than 1,000 times further than we can see.
Okay. On understanding the universe, how did you feel about the discovery of the Higgs boson this year and trying to understand the fundamental nature?
Well, of course, most of the experts expected it and would have been more surprised if it hadn't been found. So it's gratifying in that it's the piece in a jigsaw that people thought was missing, and it means that we don't have to go back to the beginning, and it fits together with the theories developed over the last 30 years. I have to say I was very surprised and in a sense gratified that there was so much public hype about it, because it is pretty arcane stuff. And although people can easily understand the idea of planets around stars and things like that, and dinosaurs and the other things that attract journalistic interest, to explain what the Higgs is all about is very difficult. It's well, you must have found it difficult. You've been trying to do it in your programs, and it's very hard. But it's gratifying it's attracted such public interest, because it is a marvelous achievement. But as I say, it's an achievement of technology as much as of science, because the Large Hadron Collider in Geneva is perhaps the most elaborate machine ever built. It's an amazing structure.
With lots of Canadians working on it,
Indeed,
by the way.
yes,
Indeed. I'll just take one more from Twitter before we go to the other
Yeah,
microphone. Will there ever be a consensus among astronomers on what defines a galaxy?
Well, I would say there is more or less. I think there's always a borderline between very small things. You call it a star cluster or a galaxy. But I would say that we do now understand the classification of galaxies, and we've got a fairly good understanding of how they evolve, because we can do those computer simulations, and we can test those theories not only by looking at the population of galaxies around us to see the different sort of types of galaxies and do the demography of them, as it were, but we can look out into space. We could look out, so we're looking back 1 billion years, 2 billion years, 3 billion years, 4 billion years. And if you've got a good theory, it's got to fit the data then as well as now. So we've got lots of tests which we can confront our theories with. And I think we've done pretty well so far. But of course, there is a borderline between what you call a very small galaxy and what you call something else.
That's a chronic problem in astronomy, isn't it?
Well, I mean,
look at
Pluto.
planets, planets, dwarf planets.
Yes.
Yeah.
Well, it is like the story of Pluto. Is it a planet or not? It's a semantic rather than a scientific question.
I ask kids, I say, what's the difference between a pebble, a stone, and a rock?
Yeah.
Where do you make the difference, the definition there? Anyway, yes, sir.
Hello? Yeah. First of all, I'm very excited to see Martin again. Oh, by the way, I was a student at Trinity College when Martin was a master. And
You
today
came to Trinity College, yes.
Yeah, yes. And today
you've got to live up to Newton, you know.
Yeah. And today I intend to wear my Cambridge University school jacket here in order to see Martin.
Wow.
Yeah. So my question is about the humans population and also the resources. And because I'm from China, so I very much agree with you that the human population, especially for the developed country, really grows very fast, much faster than developing country. And I think, my question is that what's the best way to give people the rationale, or what's the best way to control these, exponentially growth of population and runaway resources? Mm-hmm. And that's my question. I mean, even in China, we know that we have one-child policy, but actually, for many of the reasons where the monitoring isn't so tight, that people still born more babies. So, I mean, these populations still grow quite fast.
Mm-hmm.
That's my question.
So in other words, how do we flatten out that curve?
Yes.
How do we curb the population?
How do we control that? Yeah.
Right.
Give a good control.
Well, I mean, I think it would happen in a benign way if we educated the women in Africa and reduced the extreme poverty. Because, in fact, what has happened in most countries is that as they become more prosperous, the fertility rate has fallen. And, in fact, in Europe, it is below the replacement level. In the United States, it would be, except for immigration. And so, in most parts of the world, the population has stopped growing. It is only in the poorest parts of the world that the population is growing fast. And I would guess that in China, if they stopped having their one-child policy, you might still find that people only want to have 1 or 2 children. And so the population might stabilize. So I think the population rise is going to level off. But on the other hand, I think it does make a difference whether by the end of a century it's going to be 12 billion or 8 billion. And I think it would be better if it was going down towards 8 billion, because obviously more people, as they get more prosperous, make more demands on resources.
Thank you. Yes, sir.
I want to thank you very much, Sir Martin, for your brilliant talk. And I appreciate the political and ecological points you raised. But my question is more scientific. One of the big questions is, why is there something instead of nothing? And I think one possibility is there's always been something. There's never been a point where there was nothing. And how would you integrate that question with the speculation about multiverses and megaverses and where our universe came from in the first place?
Well, I think there'll always be unanswered questions. And if I think of the subject of cosmology during the years I followed it, then issues that were controversial when I was a student have now been settled. For instance, it was not clear there was a Big Bang at all 50 years ago. Now we can talk with confidence about the Big Bang back to a nanosecond. So that's tremendous progress. And so I would hope that 50 years from now we'll have made further progress. But what happens in any healthy science is that old controversies get settled. But then that allows you to pose and address questions that couldn't even have been posed beforehand. I mean, the issues we talk about now, about is eternal inflation correct and all that stuff, no one could have understood that sort of question at all 40 years ago when I was a student. And we hope we will make more progress. But as to whether there's an infinite past or how it all started, then we may eventually come to a final solution, but more likely perhaps we'll always have new questions. Or the other possibility, as I said, is that we may find that there are answers, but they're beyond what human brains can understand.
Which brings up another point of view of some groups who would say it was divine intervention that did this. And you say in your book that religion and science do not need to conflict. What do you mean by that?
Well, I mean, obviously, if people think the world started 6,000 years ago, that is not tenable. But I know a lot of English bishops, including the Archbishop of Canterbury, and he's quite relaxed about the multiverse. There's no problem there. So I think most of the more sophisticated adherents of religion are quite relaxed about science and evolution, etc. They just interpret the world with a sort of extra feature to it, but they don't say anything that conflicts. So I do feel there can be peaceful coexistence. I have no religious belief myself, but I don't think we should fight about it. And in particular, I think that we should not rubbish moderate religious leaders like in the UK the Archbishop of Canterbury, because I think we all agree that extreme fundamentalism is a threat, and we need all the allies we can muster against it. And I would regard the leaders of the mainstream churches as being on our side in that battle. And so that's why I think people like Dawkins do a great deal of damage by rubbishing and antagonizing people who should be on their side.
Yes, sir.
Well, I'm going to have to readjust my question because you just took it out of my mouth. Sir Martin, have you ever met Paul McCartney? No. Maybe perhaps a little bit more into that aspect, because I'm going to stay with it. My name's Brent, and I'm a local filmmaker, and I'm very interested in metaphysics. And for me, Einstein's E equals mc squared is his second greatest saying that he made, and the other one was, I never arrived at my understanding of the universe through my rational mind, which indicates an intuitive something else. So you, as a man of great intellect and putting your entire consciousness out there into the universes and spending your life looking for order and designs and patterns, is there a part of you that senses, and I'm not talking ecclesiastical religion, but senses a creator or senses some order that defies just the coming out of the mass and the human part of it? Is there order?
Well, of course there is order, and there's a reaction of wonder and mystery to the complexities we see in nature, in the biological world and in the cosmos. And I think anyone who studies science feels that wonder and mystery. But I think we should just accept that most of these things are too hard for us to understand. It seems to me it's arrogant rather than the reverse to say that because we can't understand something scientifically, we've got to invoke something supernatural. We've just got to think longer and harder. Most things, even quite simple. We can't understand the common cold. We can't understand many features of everyday life. And so we shouldn't expect to understand all these deep mysteries. We've got to be very modest about this.
Yes, sir.
Hello, my name is Bram. I'm a Gemini and a sci-fi junkie. My question deals with the part of your presentation that was about the global village and more so even the global idiots and
Yes.
the difference between 20 billion vegetarians versus 9 billion carnivores, which I don't care if you do either. But can you tell me if there is any interest for you within the monetary economy versus the resource-based economy, and that if we moved into that, then maybe we could feed the world and even have the resources to go into the stars like you're proposing, instead of it being just monetary-based and money and cost and et cetera?
Well, I mean, I think it is clear that our system is failing, as we've seen recently. But I think the reason why the impoverished countries are not being helped enough is a moral question. I mean, the so-called bottom billion, people living on less than $1 a day, that their lot could be alleviated very easily, but it is not being done. So I think it's a matter of morality as well as of economic efficiency. But the other point you mentioned about the village idiots, etc., I think this is going to be a greater challenge to governance than we've had to contend with in the past, because it is the case that a few disaffected individuals can produce global disruption in a way they couldn't in the past, because they're empowered by technology, biotech, etc., and we live in a networked world where we are more vulnerable. So I think that's a big problem. And I suppose selfishly, that ought to provide an extra motive for reducing the number of deeply disaffected people, and implying that even in our own interest we should do a bit more to ensure that people living in Africa, etc., who see what life is like here on the internet but can't share it, are less disaffected. So we have a motive of self-interest as well as of morality to try and spread the benefits of globalization more fairly.
Can I add to that?
Mm-hmm.
What do you feel will be the role of social media in exactly that? Because I was in Africa recently, and everybody's got cell phones.
Yep.
It's totally gone to cell phones. Yes. In spreading that word, what effect will that have?
Well, I think it is a wonderful development. I mean, in Africa and in India, of course, cell phones are spread everywhere. There are certainly more cell phones and toilets in both India and in Africa. It shows the patchiness of development. But they are wonderful, empowering things for the Africans. I mean, for instance, an African farmer can now avoid being ripped off in the market because they can find out what the prices are and things like that. And people have developed ways of getting sort of micro money transfers via mobile phones. And I think one could do some education by that. So it's wonderful. And this is going to be an educational aid. But, of course, it is going to, I suspect, lead to greater embitterment, because they all know the contrast between the life they are compelled to live and the life we live here. And I would have thought that's going to, quite rightly, make them feel aggrieved.
Yes, sir.
So, Martin, my name is Lloyd. I was wondering if you see that discoveries on the very, very small scale, such as the confirmation of the Higgs boson, have an effect on science on the very, very large scale, or vice versa?
Well, I mean, they certainly are crucial for a sort of fundamental theory. And as I mentioned, we do have to eventually try to have a unified theory which brings in gravity, which is the force that's important on the large scale, with things like the Higgs boson and other particles on the small scale. And so we need that synthesis of the snake eating its tail. And in order to achieve that, we need to understand better the microworld. I mean, Einstein's theory is pretty good. We understand gravity quite well. And so if we understood the microworld better, we would be more likely to head towards a unified theory. Because there are all these links between the very large and the very small.
And maybe that'll get us warp drive.
Maybe. Well, of course, as I said, we must keep our minds open to things that seem like science fiction.
Absolutely. Yes, ma'am.
My name's Susan, and thinking about the snake eating its tail, there was a recent article in Maclean's magazine where a scientist was talking about the universe and the other term, it's just gone from my mind, the multiverse. And he was saying that part of the solution would be if you could get scientists from opposing disciplines to work together more. And coming from an academic background, how do you get physicists to work with biologists, chemists to work with astronomers more? Because he was saying that they're just so enclosed in their own little worlds. And I know that people just go in their offices and close their doors. How do we make them work in a more interdisciplinary mode?
Well, it's important, and that's what this particular organisation that's hosting us is trying to do, I think. I think it is important. I mean, for instance, I'm at Cambridge University, where I think we do a pretty good job because the university is broken up into colleges and all the faculty belong to a college. So each college is a microcosm covering all disciplines, and people do meet for lunch every day, etc. And I certainly agree that it's a deficiency of the current academic scene that everyone is channeled into research in a narrow area. Of course, to a certain extent, if you want to make progress, you do have to focus, because it's only cranks or geniuses who try and solve the big problems in one go. You've got to solve things in a piecemeal way. If you ask a scientist what they're doing, they don't say they're trying to cure cancer or they're trying to understand the universe. They tell you about some rather specific sounding thing they're doing, which is a step towards it. But having said that, the risk of doing science professionally is that you forget you are wearing blinkers and that what you're working on is only worthwhile insofar as it's a step towards understanding the big picture. And that's incidentally why it's, I think, good for scientists to talk to general audiences, because the questions that everyone quite rightly asks are the big questions, and we need reminding often when we are in our little specialist burrows that those big questions are the important ones.
Although it's not as bad as it used to be, because we have sciences now like astrobiology, organic chemistry, they're crossovers.
Yeah.
They're
no, indeed, and lots of the action is on the interface between traditional subjects. Yes.
Yes. Mm-hmm. Okay. Yes, sir.
Hi. I would love to hear your thoughts on Moore's Law and the significance and maybe the prospect of continued exponential growth in computation.
Exponential growth in computation?
Are you familiar with Moore's Law? So like the
Moore's Law and how far can we go? Is that your question?
Of computation and the like. Okay. Yeah. Thank you.
How far? Yes. Well, I mean, I think, as you probably know, in terms of density on chips, then probably the law can only apply a few more years before you get down to the atomic scale. But there may be three-dimensional ways of storing the data, and then there's the possibility of quantum computers. So I think there is the potential of further developments. But the question is, how can we make use of this huge computing power, and how can we program them so as to assess and store the information properly. I'd like to say in my subject, computational simulations have been transformative. We can't do experiments, but we can now do realistic enough calculations to really help us. And I think simulations are going to play a big role in other subjects. I mean, for instance, in developing drugs, and perhaps in finding a high-temperature superconductor and problems like that, instead of doing zillions of different chemical experiments, maybe one could do all the simulations more quickly. So I think more and more problems will be transformed into computational problems from experimental problems. But of course, perhaps you're thinking about how computers will relate to human intelligence. I think that's a different question, how they, whether they will actually simulate the human brain. And of course, in California, there are these people who think that computers will take over in about 30 years. Yes. The singularity, they say that there'll be a computer or computer network that surpasses human intelligence. And when we've made that machine, that's the last machine we will ever make, because it'll be the computers that then make the next, even more intelligent ones. So this is a concept evangelized by Ray Kurzweil and other people
Yes,
like
indeed.
that. He's one of these people who freezes, who wants to be frozen when he dies.
He also wants to download his brain into the
That's
computer.
right, that's right. Yes.
And the answer will be 42. We have time for 2 more questions before we wrap it up. Yes, sir.
Proton is part of an atom, neutron, electron. Protein's something entirely different, but without protons, there would be no proteins.
Yes.
My name is Tom Constabaris. Sir Martin and I have probably the worst question in the world. Do you think humanity is a species the way we are going now? And you answered half the question with the computers and downloading our brains. But the way we are now as a species, do you think we will survive the next millennium with all that's going on?
The question was, will the human species survive the next millennium? I think, well, 2 things. I think it will be a bumpy ride in the next century. I think there will be setbacks like a nuclear war or something as bad as a nuclear war, and we've got to try hard to avoid that. If we look ahead several centuries, then I think there will by then be communities living away from the Earth, on asteroids or on Mars, etc., and that will indeed be good news, because that will mean that whatever happens to the Earth, there will be a future. And then I think those people out there will develop into new species, because they will use genetic modification, redesign themselves to match the alien environment. So I think a few hundred years from now, we'll start having the post-human era of different species. And also, of course, going back to the earlier question, we will probably have silicon-based intelligences, and the question is whether the future lies with them or with organic intelligence. We don't know the answer to that one.
And those new people will be known as Homo Spacians.
Right. Right. Yes.
I made that up.
Yeah.
Our last question of the evening. Yes.
Yeah. No pressure at all, thanks. Good evening, Sir Martin. I'm Andy. And in regards to a statement you made earlier about it's better to read first-rate science fiction than to read second-rate science, what do you consider to be great science fiction, or are there any authors in particular?
Okay.
What do you consider the great science fiction?
Yes. Okay. Well, let me say I'm not a great reader, but if I could say one of the greatest classics of science fiction, which I'm not sure is well known here, the works of Olav Stapleton in the 1930s. He wrote a book called Last and First Men about the far distant future, which actually inspired Arthur C. Clarke. And another book called Star Maker, which is and the Star Maker is a creator of universes. And if you look in that, you have the idea of the multiverse and the exfoliating universe and all kinds. That's a wonderful book. But the other thing I'd say is that I don't read a great deal of science fiction because it's often not well written. The characters aren't well deployed, etc. What's interesting are the ideas. And I think we need more books that condense the ideas. And I'll give you one example. There's a very good book by 2 friends of mine, Ian Stewart and Jack Cohen, called Aliens, which condenses the plots of about 100 science fiction books on aliens. And that's the kind of book I enjoy reading, because you can get the key ideas. And I think what's inspiring about science fiction is the originality of the ideas rather than the plot lines and the writing. So I would encourage more science fiction experts to write these condensed works for people like me to read.
Very good, very good.
Yeah.
Thank you.
Yeah.
Thank you all. Thank you all for your questions tonight. Thank you.
So, first of all, Sir Martin, thank you for a very thought-provoking talk and for a wonderful exchange with all of us. It was absolutely wonderful. Thank you, Bob, for moderating. Thank you to the Vogue Theatre, CBC Ideas, and Georgia Strait for partnering with us. And finally, and to my own staff, who have done an amazing job with this. And then to all of you for coming and joining in this wonderful conversation. So safe travels, and thank you, Sir Martin.
Thank you.